All right, continuing on section 3.2, we've talked about the coefficient of determination and how to interpret it. And then I tried to explain to you guys where the formula comes from. Whether that sinks in or not is not that big of a deal, but you do need to know how to find it and interpret it. So let's do an example. SEC football. The table below shows the average points per game and the number of wins for each football team in the Southeastern Conference in 2011. So you can see Alabama and Auburn and all the teams and how many points they had per game and how many wins they won that season. Create a residual plot of the linear model that uses points per game to predict the number of wins and determine if a linear model is appropriate. So I already have my data in the calculator. If you want to just watch, you're free to do that. If you want to put it in your calculator and follow along, pause it. But I think well, whatever you want to do, okay? But I'm just going to go here. So first of all, we need to see if a linear model is appropriate. So let's take a look at the scatter plot, always. I'm using points per game, how many points they scored per game on average, to predict how many wins they made. So this is if I were to describe this distribution, I would say there's a fairly strong positive linear association between points per game and wins. So, it says, is it appropriate? One way is to just look at the scatter plot and say the scatter plot looks linear. Another way to do it is to do the regression line and look at the residual plot. So let me just review how to create a residual plot. I like to open up a new window because I like nice big residual plots. And I'm going to plot my original X, but instead of putting in wins, I'm going to plot it versus the residuals. And as you can see, there's no leftover pattern in the residuals. For low numbers of points per game, my prediction's above and below, and then for medium, that's above and below. So that's another reason why a linear model is appropriate. So, determine if a linear model is appropriate? Yes. Actually, it doesn't say to justify, but come on, we got to justify everything in stats. So justify because the scatter plot. Don't just say the scatter plot. What scatter plot? The scatter plot of points per game versus wins is approximately linear. That may sound ridiculous, but determine if it's a linear model. Well, yeah, it is because it looks linear, but whatever. That's the justification. Or you could say because the residual plot has no pattern. Find and interpret S, the standard deviation of the residuals. So again, on the AP test, we probably won't have to do this. They'll probably just give it to you. But on my test, you got to be able to do it. There were two ways to do it, an easy way and a more difficult way. So let's go with the easier way. And you need to remember this. I'm going to go to stat tests, and I'm actually going to run this weird linear regression t-test. Put in your x's, put in your y's. Don't change anything else. We got some weird stuff here that we're going to talk about later in the year. But right here, that is the standard deviation of your residuals, 1.2. Or 1.2 wins, I would say. You don't need to go that many decimals. Interpret it. That is the average error in your predictions. When using a linear model with points per game to predict wins, our win predictions will typically be off by about 1.2 wins. Meaning, if you score 30 points per game, I'm going to predict your number of wins is right here, but I was off by about, looks like maybe about 1 or 2 wins, right? Here, I'm not off by much at all, but on average, I'm going to be 1.2 wins away from the true value. Find and interpret the coefficient of determination. Now, when I ran, oops, what did I just hit? Now, when I ran my linear model, I just opened up something by accident, sorry. When I ran my linear model, it calculated the R value, so I could take that R value and square it, or it actually stores the R squared value. That is the coefficient of determination. It's a popular measure, so they store it It is 87.6%. R squared is 87.6%. And to interpret that, we say 88% of the variation in Y is accounted for by the linear model that uses points per game to predict wins. And again, because I've done this for several years now, the 88% of the variation in wins. I don't know what to say. You have to say variation in Y. A lot of people say 88% of the variability is accounted for by the model. No. Variability in what? Variability in the things you're predicting. So just try to get it right. Extra note, not part of the interpretation. Meaning, so if 87.6% of the variability is explained, of the variability in wins is explained by the linear model, that means 12% of the variation is left over. That is, 12% of the variation is left over in the scatter plot of the residuals, meaning 12% of the variability is left over in some of these other variables. Who knows? The difference in offenses and defenses, the home field or away, or away advantage or disadvantage, or coaching or day of the week, or whatever other variables there could possibly be. Okay? All right. Getting information from computer output. So on the AP test, you will do a lot less of the actual calculator stuff than we do in class usually. They're usually just going to kind of give you a computer output that gives you all of that stuff, and then they'll just ask you to interpret it. So here's computer output from two common programs, Minitab. This is what I use in class sometime, and then this is JMP or Jump, which I don't use as much, but I'm starting to. I don't know. I should start having you guys get one of these programs and start having you use them in class, but I'm not there yet. So here's what it looks like. We got our predictor, and then we got our constant and our miles driven. So this is some different context here. I don't even know what this is context of. But this is basically your X variable. We're using this as a predictor to predict, I don't even know what the output is on this thing, to predict your Y values. So this is the coefficient of your miles driven, and then this is the y-intercept. So this is the slope, and this is the y-intercept. So my equation is going to be y predictor is 38257 plus 0.16292 times miles driven. That would be the regression equation. For right now, these things are just things you got to get out of your head and just kind of throw them out. We'll talk about them later in the year. This is the standard deviation of the residuals, S, and here's our R squared. Notice they do not give us the R value. To get the R value, we can take the square root of this. Don't forget the plus or minus, and then the plus or minus would be determined by the sign of your slope. That's a tricky thing you're gonna have to watch out for. R squared adjusted, again, don't worry about it, throw it out. So a lot of extra information, but the core information is there. Here, we got our R squared adjusted, throw it out. Root mean square error. Ooh, root mean square error. Okay, I guess that's what they call the standard deviation of the residuals. And number of observations. And then we have the kind of a similar, so this is a little bit different, but this is kind of the same. We got our intercept, we got our miles driven, we got our slope. Oh, look at here. Now we got a negative, and here there was no negative. Probably a typo, whatever. Again, throw all this crap out for right now, okay? So basically from this computer output, you should be able to find all the stuff you need, okay? 5 minutes, so I got time. Let's do one example here. Netbook battery life. Netbooks are a hybrid of laptop computer and a tablet. They are smaller and have better battery life than a traditional laptop. They also have a separate keyboard, unlike most tablets. Blah, 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 whatever. So they did a study. Among the variables measured were battery life and weight in pounds and cost. Computer output for linear regression is displayed along with the residuals. So battery life, weight, and cost. That's 3 variables. They really tell us what we're predicting here. So it looks like, So we got weight is our X, so we're using weight to predict hours of battery life. I don't know where cost came in, whatever. Should we use a linear model to predict battery life of a new netbook based on its weight? Justify. Okay, so first of all, is a linear model appropriate? Notice they didn't give us a scatter plot. They didn't give us an original scatter plot of weight versus hours, time that the battery lasts. But they did give us a scatter plot of weight versus the residual of your hours. This is a residual plot. So I don't know if my original looked like that or if it looked linear. But if there's no pattern left over in the residual, then I know a linear model is appropriate. So should we use a linear model? Yes. Justify. The residual plot of this linear regression has random scatter, or has no pattern, I guess, whatever, however you want to say that. So a linear model is appropriate. I can't write, I'm sorry. I'm going too fast, slow down. A linear model is appropriate. Part A. Find the least squares regression line. Okay, so now I got to look at my computer output. Weight, that's my predictor, that's my X, that's my slope, that's my Y-intercept. So hours, that's battery life. So life, life in hour, I guess we could say hours, my predicted hours. So my predicted hours is 7.944 times the weight minus 16.046. How accurate will our predictions be? Well, we can kind of describe this two different ways. We could look at the R-squared value and talk about the percent of variability accounted for by the model. But that just kind of gives me a percentage of variability. It doesn't really tell me how accurate my predictions are. A better way to describe the accuracy of my predictions is the R-squared value. So how accurate will our predictions be? Our predictions when using a linear model with weight as the predictor. I don't know if this is a needed statement, but I'm not going to risk it. Our predictions will typically be off by our battery life predictions. Our battery life predictions will typically be off by R squared, 1.6, we'll just say 1.6 hours. So when we use our weight to predict the time, the battery life, our battery life predictions are typically going to be off from the actual by about 1.6 hours. Sometimes it'll be more, sometimes it'll be less. Okay, so I think that's how we use computer output. Didn't notice I didn't have to do anything on the calculator. It's all just interpretation. That's kind of how the questions on the AP test are. All right.